Uh, Now we are going to be talking about the normal random variable that's not necessarily standard normal random variable, meaning the mean could be different and the standard deviation could be different. To be able to calculate the probabilities, which is our objective, you ought to be able to relate that one with the standard normal for which we have tables. So we're going to use those tables. The principle in general case on any normal under variable will hold again. So the total area under the curve will be 1. That is not going to change. The curve is, of course, going to be slightly different, but it's going to look like a bell curve again. It will be centered at the mean. So whatever the mean is, like a height of 18-year-old male, it will be 70. Something else like an IQ might be 100, things like that. And the curve will be symmetric. The curve will be symmetric with respect to the with respect to the mean. Sorry about that. So the another thing will be that the standard deviation back and forth from the mean, you will find an inflection point. So for example, if the curve, the bell curve looks like that, you were driving a left turn, right turn, left turn. So somewhere here and somewhere here, you are switching the turn from left to right or right to left. Those are the inflections. There'll be exactly standard deviation away from the middle. So the middle is whatever the middle is. So this is going to be standard deviation. This is going to be standard deviation. My picture is not very good, but that's the idea. Now the empirical rule will hold again. So if you go standard deviation back and forth from the mean, you will find the 68.3% of the area. If you go 2 standard deviation back and forth from the mean, you will find 95.4% of the area. And if you go 3 standard deviation away from the mean, you will find 99.7%. So whatever the curve is, so like, curve could be like that. So the standard deviation, so this is the mean here. Something else, perhaps in case of a different random variable, different normal random variable. So this is where you're driving straight, so that's a 1 standard deviation away from the mean. If you go 2 standard deviation away from the mean on either side, the area underneath the curve, this area would be 2 standard deviation away from the mean, 95.4%, or 0.954 approximately. So that means that this sliver here and this sliver here would be approximately of 2.3%, and a total of 4.6%, right? The leftover of whatever the central area is. This is just for the central area in empirical rule. Okay, now if we are looking at the standard random variable, all of those rules apply, except of course the mean is 0 and the standard deviation is 1, which is for the standard normal random variable. If you have a different curve, different normal random variable, then again the shape is going to be the same, but there are different things about this random variable. First of all, the center is at 5 because this one has a mean 5. Standard deviation is 3, which means when you look at the center and you go this way 3 and this way 3, you will find those inflection points. So that when you're changing from driving left to driving right turn, from driving right turn to driving left turn. So that's a standard deviation. This standard deviation in our case is 3 for this particular one. So you can actually read it from the variable. Of course, the height also is lower. And then this one is taller, like a 0.4. This one is lower, like a 0.13 or so, right? So it changes. There are some changes, but the shape is the same. Okay. Now, and again, as I said, an empirical rule would be applicable. So if we are looking for 3 back and forth from the mean, so that will be between 2 and 8. This area is 68.3%, right? standard deviation back and from for the mean. So this is the 68.3% of the area. So which means something here also, which adds up to approximately 32.7%. Anyway, so how do you relate that? Well, you relate it by using a scaling. So we're gonna scale that. We're gonna move it backwards. So the 5 has to go back to 0. So you're gonna subtract 5 from any z value. You're gonna subtract 5. You also have to squash it a little bit. So you're gonna have to divide with standard deviation. So you're gonna have to squash it threefold because this one is 3 times wider than the standard normal. So this is a known thing in pre-calculus. I'm not going to bother you with that in terms of transformations of the functions like we do that in the pre-calculus. You don't have to study that. But to get the story about z, you need to change the all numerical value had to be changed from the x value, whatever the x value is, the random variable value, by subtracting the mean of that random variable and dividing with standard deviation. So for example, if I'm asking you what is the z value of the height of 76 inches, what are we talking about? We're talking about the height of 18-year-old male, which is a random variable, normal random variable, that has 2 parameters. So this is how we label that, right? It has 2 parameters. The first parameter is the average height. The average height is mean of this normal random variable, and it's 70 inches. And then we have standard deviation. So it goes from, from male to male changes. The height is not always the same. The standard deviation is 3. And we write it this way, right? We write variance here, which is a square of standard deviation. But we don't write 9. We write 3 with a square, so that this is variance and the standard deviation is 3. Okay, so if I'm telling you that some 18-year-old male is 76 inches tall, which would be 6 feet 4, right? 6 foot 4. What is the z value of his height? Okay, the z value of his height is 76 is his height, minus 70, which is the mean, divided with standard deviation, which is 3, yeah? So it would be 76 minus 70 divided with 3, that's 2. 2. The z value of his height is 2. What does that mean? Well, it means that he is 2 standard deviation away from the mean. He's taller than the average 18-year-old male, which would be 70 inches tall. He's 76, so he's 6 inches taller. That is 2 times standard deviation away from the mean. The standard deviation is 3 and the mean is 70. So 76 is 2 times 3 away, taller than the mean. Okay? So that's what the z value tells you. You're 2 standard deviation away from the mean. If the z value is 1.3, that means you are 1.3 times standard deviation away from the mean. If it's a z value could be negative. If z value is negative 2, that means you're 2 times standard deviation below the mean, shorter, right? In case of a height, when we're talking about height. Okay, so let's just do one example like that. What is the probability that 18-year-old male is anywhere between 70 and 76 inches tall? Okay. First, we're going to write it in terms of a question about the probability in case of a original random variable. And again, original random variable, the height of 18-year-old male is normal. So I'm writing this labeling system again, normal. You can write x, and you can be more specific and say normal with a mean 70. So the first number you write in this list of parameters is 70, comma, and then you write the standard deviation. You put a square to that, and that's how you label the normal random variable that has a mean 70, an expectation 70, and standard deviation 3. So the question is, what is the chance that the random 18-year-old male, x, is between 70 and 76 inches tall? So this is the original question, right? This part here. Now, you're going to turn that into a question about z. It's easy to do that. So first of all, to get any z value out of any numerical value here will be by subtracting the mean and dividing with the standard deviation. So if you do that, this is the formula. You subtract the mean, whatever the mean is, in our case 70 of course, and you divide with the standard deviation, whatever the standard deviation is. In our case here, it's 3. And that's how you get the z value. So the z value of the x is just a z. So this is just a z. Right? When you have a particular number in question, like 76 for example, then you have to do the calculation. 76 minus 70, that's a mean, divided with 3. That's going to be 2. Or 70 minus 70 divided by 3, that's going to be 0. Now, you might have a question here, how is this equal now? Okay, I understand, I turned that everything into z value, but why would this be equal? Here's a very simple explanation. If I told you that x is bigger than 3, okay, would you know something about 2x? I think most of people will say, I mean, if you know any algebra, you would say, oh, 2x must be bigger than 6 then. Okay, this is your regular algebra. Everything is certain. If x is bigger than 3, I'm 100% certain to write something like that, if this is true, of course. X is bigger than 3, that's 100%. 2x is bigger than 6, that's also 100%. Now, let's say if I told you about probability, if I tell you that I am 70% sure that x is bigger than 3, meaning I believe that x is bigger than 3, but I'm not entirely sure about it. I'm just 70% sure. Well, then you have to say that I would be 70% sure that 2x is bigger than 6. Because whenever x is bigger than 3, 2x is bigger than 6. Which means that the certainty or the probability of this expression is the same. So if you do the algebra here, you can add to both sides the same thing, right? What is the chance that x plus 1 or x minus 1, if you like, is bigger than 3 plus 1 or 3 minus 1? Again, the same chance. Nothing changes in terms of probability. So again, that's why this probability here and this probability here are the same. Because the expression here is equally true or equally false as this one here. So if x is between 70 and 76, then the x minus the mean divided by standard deviation is between 0 and 2. With the same probability, just because of this. Again, the same logic applies. That means that probability doesn't change. And that's now beauty, because at this point we have tables. Okay? Now you need to know what you're looking for in the tables, and this is the story we had last time. In the tables you're looking for the area standard normal around the variable center is 0. This is where you're driving straight, so this is 1, and this would be I guess 2. So in the tables you're looking for the area between this and this area. Okay? The tables have only left tails. So you're only going to be able to get up to here, and of course up to here. This area you can get from the tables, and this area you can get from the tables, because there are left tails in the tables. Well, we're going to get the area up to 2, because we know that this piece here is 0.5, because of symmetry, right? The half under the curve. The whole thing under the curve is 1, as in 100%, so this is 50%. So then I just need to find out what is this piece here, and I will subtract 50% from that. Okay, so I go to the table. The critical value is 2. Okay, I go to the table and I will find the critical value that is 2, right here. Of course, the table also has the second decimal, so critical values in the tables are with 2 decimals. And my answer here in the table says is 97.72%. 0.9772. 4 decimal approximation. All of these values are approximation. This is not exactly 4 decimals. They are just approximation to 4 decimals. But I get 0.9772. So which means that this whole thing here is 0.9772. So that's how I got this guy. I got by subtracting 0.9772 minus 0.5. 97.72% minus 50%. Turns out to be 47.72%. So we get the answer here. Okay? The chance of a random 18-year-old male to be of height between 70 and 76 inches, between 5'10" and 6'4", is approximately 48%. If you want to round this to the nearest percent. Let's go another one. Garden or a garter snake. And the garter because it has a distinguished pattern on the back. But this is a typical garden snake. If you run into any snake in garden, it's most likely going to be this one. If it's something else, then you better run because it might be something worse, right? This one is not very big. It's mildly poisonous, but not to humans. Humans do not suffer from the poison unless you're allergic. And the average length of the adult one is 22 inches. It's slightly less than 2 feet. The standard deviation of the length of adult one is 5 inches. So they vary. They're not all the same length, right? So we also know that measurement of the living beings in wild are generally distributed normally. So we can rely here that we have normal distribution of the length. Okay, so we are talking here about a random variable that is a normal random variable, but it's not a standard normal random variable. It's just a different normal random variable. This one in particular has the mean of 22 and the standard deviation of 5. And we write again variance here, which means the variance would be a square, 25, but we don't write 25, we just write 5 squared, so that you know it's a standard deviation of 5. Okay, so again, I might have a question. For example, I run into some garden snake and I'm sure, or you know, it was longer than 2 feet. Okay, it's like a big one. Yeah. What's the chance of that for that to happen? That you can run into a garter snake that is longer than 2 feet? Well, in inches that would be 22. So you have to turn everything, of course, in inches because your parameters are given in inches here. 2 feet will be 24 inches. So this is the question here: probability that the random garter snake is longer than 2 feet, 24 inches, and I have to turn that into z question about z, that I can use tables. X just changes to z. I'm subtracting the mean, dividing the standard deviation. I'm getting z. The same thing I have to do with 24. 24 minus the mean 22 divided with standard deviation, which is 5. The exact value I'm getting is 0.4 here. So if you divide 2 with 5, you get 0.4. I'm going to use decimal here. And now I have a question about z, which is the time that I can start using the standard normal tables. And again, you need to make sure you understand what you are calculating. So you have a little picture like that. It's not necessarily going to be anything very precise, but give you an idea what you're doing here. So you have 0 here. You also have, let's say 1 is here. So this will be 1. And I'm looking for bigger than 0.4. So this is the variable axis, the x-axis, or z-axis in this case. 0.4. So 0.4, I think my idea about 0.4 would be like here. It's, I don't know. I'm getting 0.5. I need to get 0.4, which is slightly less than 0.5, right? So maybe like this here, closer to 0. So this is 0.4, and now I'm looking for the area. The area, this one here. It says bigger than 0.4, right? So I'm talking about bigger than 0.4. So this is the right tail. And I just said before, when we were looking for the whole story about the table says that they have only left tail. So I'll be able to calculate this, but I'm not going to be able to find this in the tables. However, this is no problem, because once I know this, I will know this, because they're complementary. So if this is 60%, this will be 40%. Or if this is 70%, this will be 30%, right? So I'm just going to have to subtract from 0. So I need to find out what is this, okay? And I'll go into the table. So this is 0.4 here. Critical value is 0.4. I will go into the tables, and I'll be looking for 0.4. And 0.40, right? 0.40. So this is the second decimal here on the top of the table. I'm getting 0.6554. Okay, that's the left tail. So this is not anymore a question mark here. I'm having the value of 0.6554. You will notice that in the equation I put the approximation sign, and the approximation sign is of course because the tables are 4 decimal approximation, 4 decimals after the floating point approximation, not exactly the same, so that's why I have here approximation value. But this is about this area, and I'm looking for this area, so which means I have to subtract this piece from 1. And when I do that, I ended up with the 34.46%. So this piece here, this area that I was looking for, is 34.46%. Or if you go to the nearest standard percent, 34.5%. The chance that you're going to run into a garter snake that's going to be longer than 2 feet is approximately 34.5%. Okay? Let's go one more. IQ. IQ is a test result. So if you take an IQ test, and you have to be a licensed IQ test, I mean something that would involve a licensed psychologist that can do the test like that. And then you take the test. It will take probably 3-4 hours, maybe even a couple of days, and you will get your IQ. The IQ is not the same every time you take the test. So you might have multiple IQs depending how many tests you took. It's not even the same in the same day. It changes from morning to the evening, right? Your mental capacity changes, and of course changes with age. But whatever it is, it's an IQ. It's a test result. So we say intelligence quotient. So intelligence is just a test result. Now, if you never take an IQ test, you can say, I don't have any intelligence, right? And certainly you don't have an IQ. Right? So it's not a part of your brain. Like some people think it's a part of my brain. So I have tested once, I don't know whatever I got, that's it. Well, I always have that. No, it isn't. Okay, just one test result. So somebody was doing that in 1994 in Tokyo, and they found out that the average IQ of 9-year-old children in Tokyo is 109. Now the interesting thing about this, that all of those tests are standardized. So even though the test scores are not normal, I mean, there are how many questions you got right, how many you got wrong, right? So this is going to be a count. But they are curved to be normal. So they are curved to be normal, so that curve that they are curved by is with a mean of 100. So the average score on the test is always labeled as 100, and then the rest of the scores are curved, so that the standard deviation of all of the tests is 15. So the IQ test result, random IQ test result, is normal with a mean of 100 and standard deviation 15. Sometimes 16, depends on what test it is, but in general it's 15. That's how it's curved. So these are not anything that belongs to your brain. This is just test scores, and they're curved to be normal. Okay, so I'm kind of curious, what percentage of general population is less intelligent than this 9-year-old average Tokyo kid, if you can find one, right? It's just basically the average of all of the tests of 9-year-olds in Tokyo. 109. That means that their IQ is better than the average of general population. So I'm curious, what portion of general population is below 109? So now I'm asking, what is the chance that the random IQ test is below 109? Which means also the same question about probability is applicable on statistics. What portion of people taking these tests are going to have the scores below 109? And that's the question about the x, which is the standard, which is the normal random variable with a mean of 115 standard deviation. You need to change it into a question about z. So subtract the mean, divide the standard deviation, x becomes z. Subtract the mean 100 from the 109, divide with standard deviation 15, and you get 0.6 precisely. So now we have a problem about z. And again, make a picture of what you are trying to calculate. Well, surprisingly, I get a really straight line this time. The curve is not that great, but okay. So 0. Let's say this is place when you're driving straight, so that's 1. 0.6. I think 0.6 would be like here. So I'm looking for this area. Alright. Not very precise, but this area below 0.6. Again, this is where the z value are. Z values are here. So this is z-axis, right? So this is 0.6, and I'm looking for below 0.6. So here. So this is the area I'm looking for. So again, this is left tail, so it's easy to find in tables. 0.6, 0.6, oh, 0.7257. So 0.7257, right? And again, 0.6 second decimal 0. So it's this number I'm looking for, 0.7257. And again, approximation, because the table probabilities in the table are approximated to 4 decimal values. They're not exactly 4 decimal values, they're approximated. You can approximate further, you can say 73% because this is approximately 73% if you're looking for a percentage which is the 100, right? So you round it up to 73%. Okay, one more. White blood cell count. Okay, now first thing you're going to notice immediately I said count. And you can immediately say, okay, what does this got to do with the normal random variable? Because the count is discrete, while the normal random variables are measurements. They're continuous. Okay, let me argue this a little bit. So I'm going to argue that actually the white blood cell count is measurement rather than a count, because really nobody really counts exactly. Here is the trick. First of all, you're going to have a blood test. So you're going to draw some amount of blood. And what white blood cell count is that it's actually a cell count per cubic millimeter of the whole blood. Now the centimeter in metric system is approximately 40% of 1 inch. Now millimeter is a tenth of that. So this is a very small cube. If you're looking for cubic millimeter, this is a very small cube. And in that whole blood, so this is less than a drop of blood. And in there is going to be 7,500 white blood cells on average. On average. So it depends. Some people have more, some people have less. Now, these white blood cells are not all the same. Actually, there are many different types of it. So, for example, one of them could be natural killer cells, and there are different sizes. And another one is T cells. There's different sizes. They're going to be dendritic cells. Different sizes. So they're not all the same. And even among them, I mean, not all T cells are the same. They're different ones. Okay, they're not even white. They're more like gray. They don't have any color. Not like red blood cells. And so basically what we are talking about here is that you're not really going to be counting them. And because of that, we're going to actually consider this more to be a measurement, and then we can approximate normal as a normal measurement. And so that's what's going to happen here. We are approximating this as a normally distributed value, as a measurement. So this blood cell count, white blood cell count in your blood is actually a measurement. And this measurement, I labeled that here WCBC, white blood cell count. I should probably have WBCC. Well, it doesn't make any difference. We can call it X. So this is approximately normal. Again, approximately means here that I am really dealing here with a count rather than a measurement, but I'm considering this is a measurement. And so I got the normal with the mean of 7,500, the average, the mean, the expectation, it's all the same, different words for the same thing, and the standard deviation is 1750. So again, we label it this way so that we have the clear standard deviation here, nobody's confused here. Put a square here so that you know that the second parameter that is written here is a variance, but no need for squaring it. Okay, what do I know about white blood cells? I don't know, it's an average is 7,500. I think, you know, if I go between 5,000 and 10,000, I wouldn't be too concerned. Okay, the doctor's probably going to tell you you shouldn't have less than 4,000. But I guess if I'm, you know, a little less of a doctor, I'm not a doctor, so I'm a little less professional about it. So I'm going to say, I would like to have a little more. So let's say between 5,000 and 10,000. That's 7,500 is just in the middle. So I say if I have like that, I'll be okay. All right. So what's the chance that you are going to have, or a random blood test is going to be between 5,000 and 10,000? So again, we are talking about the count of white blood cells in a very small amount of blood, 1 cubic millimeter of the whole blood. Right, so this is much less than a drop of a blood. Right, 1 cubic millimeter, right? This would be 1 millimeter. I can just barely can see through between two of my fingers. Right. Okay, so this is the question. What is the chance that X is between 5,000 and 10,000? And again, I'm going to answer this question by changing all of those values into Z values. So the X becomes just a Z. What do I do with X? I subtract the mean, 7,500. I divide it with 1750 standard deviation. And instead of writing that all, I'm just simply going to call it Z. It is a Z value now. 5,000 ought to be changed. So this is a specific number here. It had to be changed in a specific number. So I'm going to subtract 7,500, the mean, divide with standard deviation 1750. My calculation shows up negative Z value of negative 1.43. Those are critical values. The critical value could be negative. Probability cannot be negative, but critical value is perfectly okay to be negative. The other one, 10,000, I'm going to use the same calculation, not the same number. 10,000 minus 7,500 divided with 1750, and I got 1.43. Okay, these are approximation, I have to say, because I didn't get exactly 1.43. I got something different. You can check your calculator, but let's do it. So I have 2,500 on the top. I have to divide that with the 1750, and my calculator says you got exactly, not exactly, but you got, calculator goes a lot more precise, 1.42857 and whatnot. I have basically rounded up to 1.43. Okay, so this is already approximation. Why do I need 2 decimals and not something better? Because the critical values in the table is only 2 decimals, so I don't really need anything better than that. Now, What am I calculating here? So again, you need to know that. This is very important. You need to know what you're calculating. And again, I have the Z curve here. I'm trying to do as nice as possible. 0 is in the middle. This is where you're driving straight. So I said this is -1. This is +1. Symmetric. And we are looking for between -1.43 and 1.43. 1.43 in my opinion would be something like here. It's a little less than a half of a 1 going forward, right? So this is the first critical value, 1.43. And the other one is -1.43. Actually, you can call either one of them first and second, doesn't make any difference. I would say this is -1.43. I don't have much space to write, so I'm going to have to squeeze it. Okay? So I'm looking for this area between these two values. Uh-oh, I lost my curve. Yeah. So now it's much worse than what I had before. I put up an effort and then just went away. All right, look at this. Let me try again. Maybe it doesn't like me to do wiggle. All right, so this is the area I'm looking for. All right. Okay, I have a couple of different ways I can calculate this area. I mean, you can calculate this area here, this sliver here. Because of symmetry, this sliver is the same. So you just got, whatever you got the calculation here for this sliver, you're just gonna double that. This is a left tail, so you're gonna find it in the table. You're gonna double that to get this guy as well, and then you're gonna subtract from 1 to get this guy in the middle. That's one way of doing that. You can also calculate this piece here. We did something similar before, and double that. Because again, because of symmetry, you will get the area you need. Or I'm gonna do something the simplest possible. I'm gonna calculate the left tail up to here, and then I'm gonna calculate the left tail up to here. I'm talking about the area, this sliver here, that's the left tail. And when my arrow says I'm gonna basically calculate all of that up to the whole thing up to here. And I'm gonna subtract it, and that's it. That's gonna be strip in between, which is what I'm looking for, this piece here. Alright, so let's go. In the table you have 1.43, 1.4, 3, 92.36%, 0.9236, 0.9236. So that's this piece here, 0.9236. Now this piece up to -1.43. Up to -1.43. I have the tables for negatives here. 1.4 negative, second decimal 3. That's why I'm using only 2 decimals, because I have tables only for 2. And then I'm getting probability with 4 decimals. 0.0764. Oh, don't forget 0, 7, 6, 4. Okay. All you have to do is now subtract these two, and you're going to get a strip in between. Again, the tail all the way up to here is 92.36%. This sliver here, this tail, is 7.64%. And what my calculator would say, let's see. My calculator says 0.9 236 minus 0.0764 is 0.8472. That's how I get this guy. And again, approximation is of course because I use tables, and tables are 4 decimal approximation probabilities. Anything you see in the table are probabilities. Everything here is going to be between 0 and 1. So it's positive, and so it's the same thing here. These are for the tails. The left tails are bigger than 50%. Positive critical values. These are for the when they are negative critical values. This is less than 50%, or second part of the table. You actually don't need the second part. You can use the first part in symmetries to get everything you need. But I have that both. So we found out that a random blood test, there's a chance of 85% to be with a white blood cell count between 5,000 and 10,000. In my view, as a non-healthcare professional, normal, right? Something I wouldn't be concerned about. Okay, let me show you how you do that. The same calculation you can do with your calculator. Okay, your calculator has ability to calculate the probabilities of normal random variables. So we have here 2 of them that we were using. 2 of them. I have too much drawings here, so I'm going to erase to have less confusion. So we calculated the one using, oh, there's an equal sign missing here. Sorry about that. All right, I'm glad I noticed that. Equal sign missing here. Okay. I might have erased that, right? Did I? Let me see. No, I just simply forgot it. Okay, as an equal sign here. Sorry about that. I'm going to have to add it to lecture later. I will upload that on Blackboard. For some reason I forgot to put equal sign here. So this is equal, of course, to this probability. And so I calculate this probability here by switching that to the Z story. Okay? Now your calculator can do either, which means you don't really have to do any adjustment. Okay, all you have to do is to second distribution here. Now these are ranges, the areas, ranges between, from, to, okay? Oh, let's see, I pressed something incorrect. So you're gonna have to go for a CDF, normal CDF, cumulative, not a PDF. Probability density function, you're gonna have a value of the height of that curve at a particular value. We don't need that. We just need the range. You press enter. What is your lower bound? So this here is 5,000. It will ask you what's your upper bound. I have 10,000 already written. Apparently I was calculating it already. It will ask you what is the mean, and it will ask you what is the standard deviation. So all of that I just written in 5,000, 10,000, 7,500, 1,750. Now if you don't have a lower bound, for example, if you don't have a lower bound, you will use something really far away from the mean, at least 5 times standard deviation because of that empirical rule story. At least 5 times standard deviation away into that direction for which you don't have a lower bound. So for example, the mean here is 7,500. If I don't have a lower bound, then I will choose like negative 10,000. It's gonna be good enough. If you don't have an upper bound, you have to choose something really big, like so the mean is here 7,500. If I don't have an upper bound, I can choose 100,000, right? Something like that. But you have to have, your calculator needs an upper and lower bound. It cannot understand infinity. Doesn't understand, I don't have a bound. And paste. So if your calculator doesn't have a menu, you're going to have to write like that. So this is normal CDF, open parenthesis, 5,000 lower bound, comma, 10,000 upper bound, comma, 7,500 mean, comma, 1,750 standard deviation, close parenthesis. And I calculate. Oh, we got, my calculator says, .8468. Oh, I'm gonna have to add 7 here, right? And more goes further, right? Slightly different than the one I calculated here, of course, because I have two approximations. Here is one, and here's another one. So it's not as precise as my calculator. Calculator, what's the difference? The difference is in the fourth decimal here. Okay, if you round, it's gonna be, if you round, it's gonna be 0.847. Okay, the same thing as here. So you can say, yeah, the difference is in third decimal, but it's really not the whole thing. It's just like, this is 68 and 72, so it's only 10,000. So your calculus is more precise, but it's not really a big deal, because if you go to the nearest percent, it's 85% either way you look at it. Okay, you can also calculate this one by using your calculator. Okay, and this is by default on your calculator. So for example, if I change all of my memory in the calculator, I'm going to do the reset here. I am going to change everything. Reset RAM. Everything is clear now, just like it was factory produced, okay? If I go for now calculating distribution by using the normal CDF, this is what I'm facing. It tells me, okay, you calculate normal CDF, you can immediately see that I have the mean 0 and standard deviation 1. That's a standard normal. Okay, that's by default. You can change it, of course. You write here 10,000, whatever, 7,500, whatever you need. Lower bound, it tells you we're going to have a lower bound -1 times 10 with a power of 99. So huge negative number. So which means basically this is for your calculator negative infinity. So all the way there in that direction that we consider to be a left tail, right? Your calculator says, oh, go all the way there to negative infinity, right? It can't do negative infinity, so a huge negative number here. And so this, we're gonna change this because we have here negative 1.43 is the lower bound. So the lower bound is gonna be negative 1.43. And the upper bound doesn't say anything, so your calculator is calculating left tails. So you are going to now get the upper bound. The upper bound in my calculation here is 1.43. Okay? The mean 0, the standard deviation 1. I'm calculating this probability, which is about z. Paste again, and you got normal CDF. Lower bound, upper bound, lower bound, comma, upper bound, comma, mean, comma, standard deviation, comma. Well, okay, look at that. We got exactly what we calculated here down there, 0.8472, a little more decimals. So actually, this is also not going to be 0.8472. We're going to be 0.8473 if I do approximation here. So my calculator says here, this is actually 0.8473. And again, we have a mistake in the 4 decimal place, in the place of a 10,000. Again, this is not a big mistake. It's just a more precision with the calculator than with the tables. So your calculator is more precise. You can use your calculator to calculate all those probabilities. Okay? But you really need to know the relation between the regular normal and standard normal, and we use that here because this is a probability in the normal where the x is white blood cell count. This is a probability of a standard normal, the mean 0 and standard deviation 1. It's nothing in particular, just the simplest one you can have. And again, the IQ, the Z story. So I was scaling that. Again, the length of a garden snake probability, the Z probability, right? Again, the height of 18-year-old male probability, the Z probability. So you always scale that to the Z, the standard normal random variable, so that you could use the tables. Okay? You have homework. A homework is on a regular place. You will calculate by either using tables and the Z values, and you have to be able to change the X value into Z value by subtracting the mean divided with standard deviation, or you can use your calculator, but make sure you don't get surprised when the question is something that is not on your calculator, right? So you have to know both. This relation is important between the random variables that are normal. They are all related to the standard normal. They are all related between themselves too, but we're gonna use standard normal for the calculation because we have tables for standard normal. Okay, the tables, these tables that I was using today are also on the Blackboard right immediately after the lecture, so you can use them. Or you can use the textbook tables also. The textbook has tables that are exactly the same. Well, not graphically, but the numbers, all of the numbers are exactly the same as my numbers here. Right? So this will be the story for this. The next time we meet, we're going to be talking about the second part of the central of the normal random variable story, and that's going to be the story about the very, very important thing that we call central limit theorem. That's the next time we meet business. All right? So I'll see you. I am closing the stream.